Hello dear students, welcome you all. In this lecture, I am going to discuss about the selection rules in weak decays or weak interactions, right? In the earlier lectures, I have discussed in details about the different fundamental interactions, and I have also covered the discussion of weak interactions in details. I told you in that lectures that these weak decays or weak interactions are basically arising because of the change in the quark flavor and because of the involvement of W or Z bosons, right? These are the mediating particles in weak interactions or weak decays. So all these things has been discussed in details, right? As far as weak interactions or weak decays are concerned, right? Now, in this lecture, I am going to tell you about some rules which are followed in these weak decays or weak interactions. So, the first rule is a selection rule for semi-leptonic decays. So, I have also covered the leptonic, purely leptonic, semi-leptonic and non-leptonic decays in the earlier lecture, in which I have discussed about the weak decays in detail. So I am going to tell you the selection rule for these semi-leptonic decays. And this selection rule is for the semi-leptonic decay of strange hadrons. Strange hadrons, we know very well what particles are strange hadrons. Strange hadrons means hyperons. We know very well that strange hadron hyperons plus kaons. These are the strange hadrons. We know very well, as I was saying, that the hadron is the collection of mesons and virions. But I am talking about strange hadrons. So when there is a conversion of a strange hadron into a semi-leptonic decay or another hadron where leptons are also produced. Semi-leptonic means in this decay I will get a hadron plus some leptons. This is the meaning of it. So in these reactions, the selection rule is delta S must be equal to delta Q. What is the meaning of it? Delta S here stands for a change in the strangeness quantum number. Change in the strangeness, and delta Q is a change in charge. So it is very clear that whatever change is going to take place in the strangeness when a quark is changing from one flavor to another, and that change must be equal to the change in the charge when a strange hadron decay into another hadron plus some leptons. Let's take an example. I have an example where a strange kaon decay into a pi hadron. This is also a hadron, pi meson, right? But it is not non-strange. This is I am talking about the decay of strange hadrons. Strange hadron is decaying into another hadron, but it is not strange. Plus electron, positron, sorry, plus electron neutrino. So when we have to look at this, reaction, we have to look at the only this part, change in this part. That in what way this strange hadron is changing into another hadron, because this particle is arising because of the coupling of W plus minus boson. We have seen the Feynman diagrams. So here in these two hadrons, delta S must be equal to delta Q. This is the rule. Otherwise, if it is not followed, then the reaction is strictly prohibited or forbidden. So let's look at here. So if I look at the K positive and this side, so K positive has strangeness plus 1, right? And as far as the strangeness of this pi naught is conserved, K positive plus 1 and pi naught it is 0 because it is not strange. So delta S means S final minus S initial. It is equal to 0 minus 1, it is minus 1. This is the change in strangeness. Now let's look at the change in charge. So you can see here charge is from plus 1 to 0. plus 1, 2, 0. Don't consider these. This is very important because here one hadron is decaying into another hadron. We have to look at only hadron component, right? Because these two particles are arising because of the coupling of this we have seen in the Feynman diagrams. I can write this as a pi naught plus W plus or minus whatever it can be. So then after this particle convert into these two particles, right? So here 0 minus 1 del Q is also equal to minus 1, right? So now in both the cases del S and del Q, they are exactly same. So I can say that this reaction is allowed, right? This reaction is allowed and it is happening with full probability because delta S is equal to delta Q. So this is the rule for the strange hadronic non-leptonic semi-leptonic decay. Let's take another example. Here lambda naught particle decay into proton, right, plus electron plus electron anti-neutrino. So again I can write this reaction as a lambda naught will give you proton plus W plus minus. Then this W plus minus will further couple with these two particles. So now when I am looking at this reaction, I have to check this rule in these two hadrons, how these hadrons are behaving. Right now, if we look at this, what is the strangeness for lambda naught? So strangeness for lambda naught is because when I am writing the strangeness delta S is equal to delta S final minus S initial. So here S final is 0 because proton is non-strange and S initial is minus 1. Strangeness for lambda naught particle is minus 1, right? So it becomes plus. Now what about delta Q? Delta Q is equal to final plus 1 minus 0. So again it is a plus 1. So again we can say delta S is equal to delta Q. So this reaction is again allowed. So this is the delta S is equal to delta Q rule for the semi-leptonic decay of strange hadrons. Clear? So this rule is applicable to all strange hadrons, whether they are counts or whether they are hyperons, because only they are strange. But they can convert into non-strange hadrons also. This is because यहाँ पे restriction नहीं है, restriction यहाँ पे. Clear? So this is the first rule. Now I am coming to the second rule. Second rule is a selection rule for non-leptonic decay of hadrons. Now here we are taking the case of non-leptonic. Non-leptonic means again the decay that we are considering here, the decay we are considering is the decay of strange hadrons. It is very important. Clear? But it is non-leptonic decay, means the strange hadron is converting into another hadron. It is not necessary that this hadron is strange, but it is converting into another hadrons, right? Strange hadron is decaying into another hadron. So for this selection rule for non-leptonic decay, the rule is delta I must be equal to 1 by 2. But here even delta I is equal to 3 by 2 can be there, but this delta I is equal to 3 by 2 is suppressed. Suppressed means this probability is very low and this is a dominant. इसका मतलब क्या है कि ये जो डेल्टा आई इज इक्वल टू 1 by 2 वाली रिएक्शंस होंगी वो डोमिनेंट रहेंगी, ये वाली सुप्रेस्ड या कम होंगी, पर हम फॉरवर्डन नहीं बोल सकते. बट यहां पे तो बड़ा क्लियर था कि डेल्टा एस अगर डेल्टा क्यू के बराबर नहीं है देन द रिएक्शन इज फॉरवर्डन, बट यहां नहीं है. Here the some reactions has been observed with delta I is equal to 3 by 2, but they are not dominant. The dominant reaction take place in this direction where delta I means change in the isospin, z component of the isospin. We can write Iz that is equal to 1 by 2, right? So this is the rule that is strictly followed, but this delta I is equal to 3 by 2 is not forbidden, even it can take place, right? Let's take an example of decay of a strange hadron, where K positive gives you pi positive plus pi naught. Now look at this, right? Because here now the particle involved are all are hadrons, right? So we have to consider all the particles, right? So what about the I for K particles? It is 1 by 2, K positive plus 1 by 2. And what for this pi positive? Pi positive, it is a 1, right? And for pi naught, it is a 0, right? So 1 minus 1 by 2, because I final minus I initial. 1 minus 1 by 2, it will give me 1 by 2. So delta I is equal to 1 by 2. Delta I is equal to 1 by 2. So this reaction is a dominant. Clear? This is dominant because this condition is fulfilled. Delta I, change in the isospin of the particle. Even once again I am saying that we can even write I z or I3, right? So but even you can observe some reactions where delta I is equal to 3 by 2, but these reactions are not dominant, they are rare in the nature. मैं एक और example ले रहा हूं. You can see here K naught meson, that is kaon with neutral, no charge, right? That convert into pi plus pi negative. Now what about it, right? What about this, right? To isospin. So in this case, what is the isospin? Change in isospin. The isospin of this particle, this one, it is a for K naught, you know very well, it is a minus 1 by 2, right? K naught minus 1 by 2. And what about pi positive? Plus 1, pi negative minus 1. So minus 1 plus 1, 0. So minus 1 by 2 is equal to 0. So what is the delta I final minus initial? It is 1 by 2. So again, you can see that delta I is equal to 1 by 2. And that's why this reaction, again, it is a dominant, right? The decay of neutral kaon proceed in this way rather than 3 by 2. Clear? So these are some examples that I took here for making it clear that what are the selection rules. So you see here we have two selection rules that are usually followed in the big decays. One is the selection rule for the semi-leptonic decay of strange hadrons, delta S is equal to delta Q, and the second is a non-leptonic decay of strange hadrons, where delta I must be equal to 1 by 2, but it means here that it is dominant, it is having high probability, but delta I is equal to 3 by 2 having low probability. These selection rules are very, very important in identifying the different nuclear reactions, calculating their probabilities, and understanding the working of weak forces and weak decays, right? So this is all about the selection rules, two important selection rules. So thank you very much.